All right, so we're gonna look at some, can you all see my screen here? All right, so hello, I'm Leah Dix-White. I will be talking with you all for the next half hour about some topics in geometry. Let's start off with KCM. We are an organization within our state that offers professional learning in lots of formats. As you can see, this is a virtual learning session. And we work with the state's teachers from pre-K to post-secondary. And so we have a lot of virtual sessions that are going on this week, many more to follow. And today is one that will be talking about similarity. And so if you want to know more about other sessions that we're having this week, you can go to the website. It's there on your screen, and we have a lot of virtual activities going on now that everyone is social distancing. So today, what are we going to do in today's session? We're going to look at a little bit of research behind the standards and behind the work we're going to do together. It's going to be all digital, and so I'm hoping that we'll treasure these waters together and looking at some visual proofs in GeoGebra. So at any time that we're going through this stuff, if you want to chat or interact, it's a small enough group we can do that. And also, if you want me to pause because I'm going too fast or go back to a certain screen, you can do that as well. On the website, there was a PDF that you could download to follow along, but I will be following along with you. So I'm hoping that we can get through this together. And we'll also look at some other virtual manipulatives towards the end, and I'll give you some information on some upcoming sessions. So what's the research behind the work that we're doing today? I was looking at a tweet from Robert Berry, who's the acting president of NCTM. He was talking about how are these math teaching practices looking in a virtual format? How is that looking online? And one of the comments from a teacher was like, it's like a virtual playground where we have multiple entry points and multiple ways to engage. And so if we can think about the math teaching practices in this way, that'll make it more accessible for everyone, including our students. And so when we're talking about this concept of similarity, we want to think about what that means in terms of transformations. And so I'm making some assumptions here, but I'm assuming that if you are a high school geometry teacher, you've already taught transformations and you've already taught similar triangles, because those are two standards that are in our Kentucky academic standards. And so we're going to talk today about how to make that bridge from transformations to similarity, and specifically talking about dilations of figures and circles. So that's where we're gonna go, and this idea of a visual proof. And so I'm reflecting on the work from Batista and Clements, and it's not recent research, but you've probably heard about it in your methods courses about those Van Hill progressions of geometry understanding. And so that's what I was referencing here with this quote. So what are the standards we're going to talk about today? And the one standard that we're going to talk about are dilations of circles, and how we're going to verify with a proof in GeoGebra, okay, that all circles are similar. So we're going to start off with two arbitrary circles, and then we're going to change their radii and then prove that they're similar, and then make this deductive reasoning that all circles are then similar. And how we're going to do that, we're going to understand these properties of dilations and understand it in a virtual way. So when you're thinking about proving similarity, especially with triangles, you're thinking about, okay, let's compare corresponding sides. Let's compare these links. So we're going to be doing that, but in a virtual way. And so I want you to think about that as we progress along. Are you guys with me? All right, here we go. So let me give you some context on what I mean by visual proof. I'm gonna show you a visual proof, and it's a proof of area, how we get the formula for the area of a circle from the formula for the area of a triangle. Now the proof goes pretty fast, but what I want you to do as you're watching this proof, think about what is specific about this proof that would help you understand it as a student and even as a teacher. So just make some mental notes. It's like a 1-minute quick video, and then we'll touch right back here in a second. So hopefully there's not a lot of ads with the video.
Your face is
And
your
there's
money
an ad,
maker.
of
So
course.
why would you
Hold on
pair
just
it
a
with cheap
second.
plastic?
One more second.
Why does
We're
some
gonna skip
plastic
this.
cost $500?
All righty, skip the ad. All right, here we go.
Word on the street has it you'd like to derive the area of a circle. Well, all you need is some chain and a ruler. And it's a visual proof, so I'll stop talking now.
Okay, that was kind of fast, but what I wanted you all to see was how, and share with me any comments you have about how visually you were able to make that connection between the area of a circle and an area of a triangle. Someone want to share? No one?
I saw how the circumference of the circle became the base of the triangle as he unwrapped all those circles that had filled the original circle, I guess.
Nice. Awesome. And so something about those pieces moving. What I like about the visual proof is that the movement behind the pieces and being able to manipulate them in different areas and spaces to make those connections. Okay, anyone else? Thanks, Cindy.
I saw the radius was the height, and that made perfect sense to me. And then when they substituted it, all of a sudden there comes the formula.
Nice. And so I just wanted to share with you that before we went on. And so now we're going to move on because I want you to think about these, how visual proofs help us and with this repeated reasoning. And so if you notice back in the standards, and I'm going to go back a couple pages to that, MP5 and MP8 are the standards that are emphasized, and the significance of those would be 1, the tools, and we're going to use GeoGebra, that's going to be our tool. And 8 is when we're looking for and expressing regularity in that repeated reasoning. And so I want you to think about that with these visual proofs as we look at 2 more examples. And so the repeated reasoning that I want you to think about is how we are proving similarity with these transformations for triangles and for circles, and how we're going to make those connections with the visual proof. So first we're going to look at the triangles. Think about what I would need to point out, or what a student would need to mention, or what metacognition would need to happen to prove similarity for both pictures. We're going to go through this together, and you can follow along with me. I have linked these into the slides. So we're going to look at the triangles first and think about those movements, just like in the video, and how the movements make those connections. So first we're going to start with triangles, and then we're going to look at circles. So this here that I'm clicking on is in GeoGebra. It's called an applet. And what's unique about applets is that they've already been created. Actually, the guy, his name is Tim Brzezinski, that creates these. And you can embed these in any activity for your students, and then they can actually participate in the visual proving. And so what I wanted to show you from this applet are 2 triangles. And we are, remember, we are proving that these 2 figures are similar from a dilation. And so what is neat is that in GeoGebra you have what's called sliders, and they can adjust links. And so then I can adjust this link to superimpose one triangle into the other. That's a skill factor of 1, so they're congruent. And then I can continue to slide to see how I am able to map the pre-image onto the image. Another thing you can do is you can calculate the distances. And so I clicked on this centimeter here. I can calculate the distance between A and B. and the distance between A prime and B prime, and then compare those distances. And I can also show there how the side lengths are proportional. And that's a concept from middle school, obviously. But then we can continue to move the slider in order to prove that I can superimpose one onto the other by doing a series of transformations. That's a triangle example, okay? Questions or inferences about that in the visual aspect of it before we look at the circle example? Okay, so here's the circle example. Once again, if I were doing this with my students, I could embed these into a document or a sheet. And so now if triangles are similar, giving proportional sides and congruent angles, what does that tell me about circles and what I can manipulate there? And so what you'll find here is that it says slide me slowly. I'm gonna slide slowly. We are going to superimpose one figure onto the other, doing those transformations. So the first transformation would be the slide, okay? And notice that when we slide, we now can compare the radii. And what's neat about this applet, it does it for us. Oh, so now that we have translated the circle, I can apply the second transformation, which is the scale factor, which superimposes them onto each other. So once again, I have the slide and blow up that superimposes one onto the other. Okay, so those are two visual proofs. We're not done yet though, but let's just think about that. When would students, or when would we need to look for or notice repeated reasoning from those two activities? Let's talk about that. What do you guys think? Any inferences as to why or how we were able to, between those two activities, think of some things that were in common? This whole idea of taking a figure, sliding it, and then applying a scale factor. And if that's true for any two arbitrary circles, it's true for all circles. And so those are just some things that I thought were interesting that we could point at with our kids, because textbooks don't always do that. And so I was thinking of what are ways we can make that connection and help kids make that connection between those two proofs. So
Leah, I always say that the power of the technology, that visual technology that you have, is that idea of the what if, and the ability to make a move and to be able to do that. How beautiful to be able to do that with our kids in that program, in that GeoGebra. Powerful, very powerful for the what if situation.
And with the triangle one in particular, you can look and do the comparison between A and A prime and B and P prime for each one of those, you know, individual moves that you've made, and sort of look what happens each time and go back and forth and do some comparison there as well.
Mm-hmm. One of the things that I think was hard for middle school kids, that then similarly should be hard for high school kids, is to think that the angles, that they could measure those angles and realize that although the figure gets bigger, the angles stay the same. And that's a mind-blowing, it's hard for kids to realize that. And so again, that beautiful technology helps me to see that in a robust way.
So I have a couple more activities. So I created a handout that I thought was really cool that you could follow along with me, or you could make a copy, give to your students, either way. But I'm gonna go here, and this is kind of walking your students through the proof. And so if you open the document, I have two arbitrary circles. So first thing we're gonna do is ask ourselves the question, are these circles similar? And then we're gonna go about proving that by first looking at the radii of the circles. So if we were to look at this in GeoGebra, and I've also made that link here, I'm just going to go through the steps with you. And while I do that, I'm going to show you how some little features of GeoGebra so that it doesn't seem as intimidating. So I've drawn a couple circles here, and you can have this link for your students. What's neat about GeoGebra, it will save links for you. And it'll also, you can cut grids on and off. Like I don't have to have this grid here, if that's, less confusing. So you can cut the grids off. So the next thing here, to find the radii of each circle, if we wanted to do that to get the scale factor, we can click on the edge of the circle, and hold on, let me go back to this screen here. I should be able to double click, and here, this is circle B, it's radius 7. Here's circle C, radius 3. And so I know that the ratio of those two radii would be 7/3. And so the question would be, how could I map one circle onto the other, or what would I do? And you can definitely do that in GeoGebra. And so I wanted to show you how to do that. First, let's look at, I'm gonna go back here. I have another applet to show you that kind of gives you some practice. So if you look at this circle applet, what's nice about this one here is that you can actually map the copy onto the original, and you can use the slider to do that. So if I'm going to determine if these two circles are similar, I can map B onto A by walking horizontally 9 to the left, and then moving up vertically 10, and then I can apply a scale factor of, what is that, 2? And I've just superimposed one onto the other. So if students didn't know how to respond, how can I transform? I can actually practice that movement, and as I refresh, it'll give me another pair. So if this is true for my pair or any pair, then it's true for all circles, and that's that repeative reasoning that we were getting to. And so students can practice that. You can have them practice that. You can also go back here and actually do that. So let's do it. And I have the steps here. So if I am to superimpose one onto the other, I can click on this circle here. And at the top, I can translate the circle of vectors. So I can click on the circle, the center, and the direction. Boom, I just translated this small circle here. And then the next step would be to dilate, applying that same scale factor of 7/3. So let's see, I can click on dilate from a point. And so if I click on this point here, and I can dilate, hold on just a second, let me move some things around. I've got to move my box here. Okay, hold on, go back. I can click on, go back here, dilate from a point. It gives you kind of the directions here. So I select the object and then the center. So here's the object I want to dilate. Here's the center. The scale factor is 7/3, right? That's the ratio of the radii. And you can't really see it, but C double prime has superimposed the small circle into the larger circle. So I think that students could do that. I think that you could show your students that, and then they could actually do the work themselves. If you go here on the handout, there's some steps to show them how they can create their own radii and do the same steps that we just did. And then there's some questions. What can you conclude about any two circles? If it's true for your circles and for mine, is it true for any circles? And then there's some extensions there. So you guys talk to me. That was a whole lot. What do you guys think about what repeated reasoning and similarity did you notice from these visual proofs? Share with me. What do you guys think? I know that was a lot.
But Leah, I just want to make sure I understood. When you were doing the, you kind of left the document and went to that other resource?
Yes.
And it was just generating a new problem each time?
Yes.
So kids could do it 3 times, 5 times, 7 times, and know that what they're seeing could be completely different every time. Yeah, I love that. I love that really takes away this element of, well, you could have chosen,
Yes.
a nice problem.
Yes, I know there was a lot at once. The document is really just to help you go through the steps, and also if you wanted to reproduce it for any reason, but it's the whole idea of if it's true in this arbitrary case, then we can make conclusions about when it's true in other cases or other instances. So did anyone else want to just share anything else from the visual? I know it was a lot to chew. So go
I
ahead.
appreciated the opportunity for the scale factor work.
Okay.
It ties into the stuff we're doing in the middle grade stuff with, reasoning up and down and the proportional reasoning. That seems like it's a numbers thing, but it's not a numbers thing. It's a visual thing, and it ties directly into the geometry. So I love that.
Nice. Thanks for sharing, Dee.
You're welcome.
Basically the repeated things that I was noticing is like, okay, triangles have proportional corresponding sides. So circles have proportional corresponding radii, circumferences, and diameters. And so then the next leap would be solids also have proportional corresponding heights and radii. And so even though our standards don't look at similarity between solids, I think it's an interesting progression from 2D to circle to 3D, the same idea of proportionality between these different linear segments. So it's the linear pieces that have those proportional relationships. I thought that was just really cool to notice that and grasping it from the context of a dilation.
Leah, one of the things that we are kind of sending out as a message from the Kentucky Center for Mathematics is now is the time to really slow down and give your kids the opportunity to explore and to set them up with some rich tasks that take several days to really ponder, because we have the time now, and we have that is a beautiful way to use technology to see those relationships, and then coming back together with the students and saying, all right, so what did people see?
Definitely. So basically it's just kind of bringing together, like the dilation is basically like the sequence of transformations that map one figure onto the other. And so then my extension to that would be, okay, so are all cylinders the same height? Are they similar? Why or why not? So
Toilet paper happens to be a big thing right now, Leah.
it really does. It's like
Very topical.
Yes, I was talking to Julie. I was like, that's what's really at the height of my mind is this toilet paper issue. But it's interesting because we can make these connections, even though similar cylinders is not in our standards. And that's another reason why I put this on here, because it was in the past. So that's moved on. We can still make those connections with our kids and give them that extension for relevance, and also to bridge those repeated reasoning ideas as well. So I thought that I would throw that in there. And also on that handout, I have some extensions with that. Some questions, just some interesting trivia. So you can check that out. Also, there are virtual manipulatives that you can check out. GeoGebra has different formats. So the ones that I was showing you were applets and the GeoGebra Classic, but it also has a Desmos platform that includes a calculator as well. So I encourage you to get on and play with those things. There's also simulations with Desmos and also .x, and those are also available on our website. And as always, thank you so much. I know we're a little early, but we had a smaller group, and just know that we're here to support all teachers, as always. And if you have any questions or comments, feel free to leave those in the chat or check out any of our resources on the website. So,
Leah, one of the things that I did was opened up your presentation, and your links took me straight to what you wanted me to look at. So it is one-stop shopping in both the presentation, took me straight to where she was. I don't have to dig around and try to find it. And the handout then is available for you guys to retrofit however you want to use with your students in your classroom. So the idea is that KCM's here to give you some ideas, some resources. And again, we say, give them one rich task and really let them come to the understanding. We like to end with giving a shout out. If some of you guys could unmute and tell me what did you like about the presentation today, and Leah's the way we're thinking about this. Julie Adams says that she's got some nieces who are having difficulty in their high school math courses, and this would be a really great support for her. it stretched some thinking of our folks. Some folks that are here today, again, reminded us of some mathematics that we haven't done in a very long time. And the technology, Cindy says the technology is fantastic. You're right, Shannon. It keeps conceptual learning moving, and especially when it's digital. I do say that the technology is one of the most beautiful ways for us to do that what if situation. What if it's another circle? What if it's, you know, how would it work if it was solid figures? So what a nice way to be able to do that. And I agree with Lisa. Lisa said that she thought that the connection to the student mathematical practices was great. Leah, that was fantastic. It really got me thinking about that's exactly the way. And of course, toilet paper math. How relevant is that right now? So, Leah, we thank you, and of course, everybody who's on today can contact you. You're a good thought partner for our teachers across Kentucky. So, Abby, Cheryl, Karen, Shannon, if you guys need anything from the high school world, Leah's here to help. KCM is always here to help our educators. Thank you.
Thanks, guys. Appreciate your time.